just try to repeat this argument. So we again imagine at very low temperatures all the spins point in the same direction, and we imagine that there is a region of size L where the spins, let's say, flip sign. So what's the usual story? Usually, you would think that the energy that it costs for all the spins to flip sign is again going like L to the power d minus 1, because that's the circumference or the area of the boundary. But this is not correct. Because there are Goldstone modes, the spins don't have to flip sign abruptly, like across this region. They can flip sign continuously. And that costs much less energy, because it comes from the gradient terms in the action for a Goldstone mode. So actually the correct answer when there are Goldstone modes is d minus 2. And that's the origin of the so-called Coleman theorem about the absence of Goldstone bosons in two dimensions. So phase transitions with Goldstone bosons don't exist in 2 dimensions in the ordinary story, right? That's what Coleman has explained, and Marman and Wigner have explained in the context of condensed matter physics long ago. And that's the origin of this phenomenon, that you can split the spins in a way that costs less energy than the discrete spin story. And now, for the same argument as before, we need to subtract d over 2. And then we get a bound which is d bigger than 4. So you see that phases with Goldstone modes disappear below 4 dimensions. So only for d bigger than 4 are phase transitions. So for example, the XY model, which is a variation of the Ising model where the spins can point in some plane, that's a very well-studied and interesting phase transition in 3 dimensions. Once you make the magnetic field random, it goes away. There is no phase transition, there is no ordered phase. Okay, so let's now try to see how to calculate.
So I said that in 3 spatial dimensions there is no phase transition.
In 3 dimensions?
3 spatial dimensions.
Yes, if you have Goldstone modes.
Well, how about Higgs mechanism?
Higgs mechanism.
The Higgs we have.
The Higgs, I mean, you are talking about the ordered phase of a system which has a Higgs field and a gauge theory?
How about pions?
Oh, you're asking about the chiral symmetry breaking in QCD.
Right, we do have Goldstone bosons in 3 possible dimensions.
That's correct. I've not said that they don't exist. They don't exist below 2 dimensions. But once you have a random field, they don't exist below 4 dimensions, including 4 dimensions.
Okay, so this is the case with the random edge field?
Yes. Yeah, this is the contribution due to the fact that there is a random magnetic field. So it gives you, you see? So what it tells you is that, okay, in the cosmos there is no stochastic magnetic field or something of this sort. Okay. Okay, so let me now explain how to tackle this problem mathematically. This is what C asked about, so how to formulate the problem, and then I will also prove this fact by a calculation. Okay, so mathematically, what you want to do is that first you can compute correlation functions. So say we have the original model, which is just the thermal field theory, and it's just the continuum version of the statistical mechanics problem, and we can calculate correlation functions. So SI prime by the usual prescription, which is that we path integrate over all the spin fields. So let me denote the spin fields by sigma. So we calculate correlation functions of phi of x1, phi of xn. So that's the usual prescription for how to calculate thermal correlation functions. Nothing. So we have phi of x1, phi of xn, and then we have e to the minus the action. The action is what I wrote before. And for the good order of things, we usually normalize by the vacuum amplitude. Okay, to remove disconnected correlation functions. So that's the usual prescription for how to calculate correlation functions. Now, what do we do in the present case? In the present case, there is some random field. So we add to the action h, phi. That's it. I'm still thinking in terms of this random magnetic field, but it could be also some other coupling that's random. So the action is deformed by h phi, likewise in the denominator, okay, where h is a given function. So now the correlation functions depend on some function h of x. So you can calculate these correlation functions for any given h of x. And the idea now is that the final averages, which I can denote with two brackets, phi of x1, phi of xn, are given by just averaging over h the previous correlation functions with this Gaussian weight. So the Gaussian distribution is realized by adding h squared over 2c squared the action. Is that visible, or should I write it in a bigger plot? So this is the usual correlation function evaluated with a non-trivial background field h of x, and then we average that with a Gaussian weight. So you see that that's different than adding an exponent, because there is the pesky denominator. And the pesky denominator is what makes this problem very hard. So it cannot be really easily reduced to a normal problem in quantum field theory.
Well, it sounds like people were doing the wrong thing for the stochastic Navier-Stokes.
Well, as you know, yes. I mean, this is where I got into this. You remember that episode? Yes. Okay, so this is the prescription. I'm not sure is it completely visible to everybody, or if somebody doesn't see it, raise your hand. Okay. So that's the main formula. And now I want to do a computation, but when the action is just free field theory. That free field theory could be the free field theory of Goldstone modes. And so the computation that I'm about to do is to verify this qualitative picture. Okay. So let's take the action to be the action of a free field. Gradient of phi squared, and that's it. Okay, and then we have this random magnetic field. So we can just compute everything. We can compute these correlation functions as a function of any background field h. Then we can average them explicitly, and the whole thing can be done very, very explicitly, which is nice, even though it's just free field theory. Okay, so let's do this. So the first thing that I want to compute 2-point functions. Okay, I want to compute phi1, phi x1, phi x2 for a given background field h of x, and that's given by the path integral d phi e to the minus s plus h of x phi of x dx, and then this needs to be divided. Oh, sorry, I forgot the two insertions of phi x1, phi x2. And this needs to be divided by the same thing without the insertions, just to get rid of vacuum amplitudes. Okay, so this is the first computation that we need to do, and that's of course very easy. It corresponds to the 2-point function in free field theory in the presence of a given background field H. So the Feynman diagram, there is this Feynman diagram, which would have existed also without the background field H. But now there is a new diagram which looks like phi that goes to H. This is an insertion of H. Okay? So this is phi of x at x1. And then there is another insertion of H. And then there is phi of x2. And these are all the diagrams that are present, because all the other diagrams would be vacuum diagrams. If you lowered this interaction from the exponent more than 2 times, there would have to be some contraction, which is a vacuum diagram. So it would be cancelled by the denominator. So the claim is that these are the only 2 diagrams. Okay, and we can just write it out explicitly. So the answer would be that this 2 point, I'm not yet averaging over the background field. This is is just a computation in the presence of a random background, in the presence of a given background field. So that comes out to be 1 over x1 minus x2 to the power d minus 2. So that's just the free propagator in d dimensions. Okay, this is the free propagator in d dimensions. And then we have some integral that we have to do over the position of this insertion and the position of that insertion. So we have a double integral over some ddz, ddw, and then there is a 1 over x1 minus w to the power d minus 2, and then there is x2 minus z to the power d minus 2. Okay? And of course I forgot the h of w and h of z. Okay, so this is the answer for the free field 2-point function in the presence of a background field h. And now to compute the double average, we just average over h with the Gaussian distribution. So we just replace this by a delta function. So phi x1, phi x2 is now given by the free propagator, which we know and love. And then there is a new term that comes from contracting these two guys, using just averaging over them, and that gives you a c squared, which is the variance of the disorder. And then there is a delta function, so we have an integral over d dz, 1 over so 1 over x1 minus w to the power 2d minus 4. Because w, sorry, no, that's not correct. So d minus 2 times x2 minus w to the power d minus 2. And the integral is over w. Okay, so that's the final answer in free field theory.
So this is the leading approximation of H?
No, this is exact.
The complete. So there's no multiple H insertions?
No, because this is the main claim, that this is exact. Why is that exact? So if you lower this interaction more times from this exponent, so there is, you need to compute the numerator and the denominator, okay? So from the numerator, you could have lowered this interaction many more times, indeed. But then at least two phi's would have to be contracted among themselves, and that would be a vacuum diagram. And it would be cancelled by the expansion of the denominator, because the division by the denominator corresponds to removing all the vacuum diagrams. You remember that result? Yes. So this is why this is exact. Okay. So of course, the first term is benign. We know what it does. It's the usual propagator, but this is more interesting. This is it for a divergent. I mean, this integral doesn't exist. It's a infrared divergent when this power exceeds that power. Sorry, when this power exceeds that power. So this is infrared divergent when the power d is bigger than the sum of those two. So it's 2d minus 4. Okay, so that means that this is infrared divergent when d is smaller than 4. That's the result that this is the same as what was obtained previously with the qualitative using the qualitative argument. So it's infrared divergent for d smaller than 4, and you see that it's very, very similar to the Coleman theorem. The Coleman theorem is really about the fact that the propagator in the 2 dimensions is a logarithm which grows, and therefore the theory is not allowed. And this is a non-trivial generalization of the Coleman argument. It's very similar. If d is exactly 4, then this is log divergent, and the correlation function is grown, which means that you have to throw away the theory.
Sorry, so what if we put the system in the compact space?
yes, I mean, you could have said that if C is very, very small, this would kick in very late. But yeah, I'm talking about, the theory, the thermodynamic limit, when the theory is in infinite volume, and then this is true. So the theory, this is infrared divergent for D smaller than 4, and for D bigger than 4, it's not infrared divergent. You can actually solve the integral, and what you get is that this double average for phi at x1, phi at x2 is given by 1 over x 1 minus x2 to the power d minus 2. And then there is c squared, and you can just solve this integral by dimensional analysis. It would be something like c squared over x1 minus x2 to the power maybe d minus 4 or something of the sort. So d minus 4. Okay, so that's the final answer when the integral converges. And otherwise, there just doesn't exist. And you see that this is more dominant in the infrared. So this is more dominant in the infrared than this. Always. Okay, so now you see that one can pose the more interesting problem. You're given some conformal field theory, which is not necessarily just free field theory, and you want to understand what happens when you take some coupling, some relevant operator to be random. So let's discuss now the more general situation. Are there any questions about free field theory? So now let's discuss what can be said beyond free field theory. So what's the general setup of the problem? We start from some conformal field theory, which has some action S. It doesn't have to have an explicit action, it doesn't matter. So we start from some given conformal field theory, and we decide that some coefficient of some relevant operator becomes random. So we say that we deform the theory by h of x times some O of x. And we decide that h has zero average, but this kind of Gaussian distribution for the two-point function. So d of d x of minus y. Okay, so that's the setup. And this is some relevant operator. And we know the dimension of O will be denoted by delta. Okay, this will be the dimension of O. And I mean, you can assume that it's a relevant operator. Otherwise, it's pretty clear intuitively that it doesn't do very much. Okay, and you can ask under what conditions on O would this disastrous phenomena take place, or maybe there's, and under which conditions would it maybe just change the critical exponents, but you would avoid such a disastrous phenomenon? So this is the kind of question that you want to pose. So one aspect of this is very easy. So as you remember, the definition of some, let's write the definition of some correlation function. So x would stand for some product of fields, which we want to average over the quantum fluctuations, namely the thermal fluctuations, and the h variable. So the path integral that defines, let's write the whole path integral that defines that. So we have dh, and then we have d phi, where phi are some quantum fields, and h is our background field. So we have h squared x over 2c squared, and this is integrated over space. I'm just writing the full path integral to make some argument. And then we have e to the minus s CFT plus h o. Then there is x. X is the product of some local operators. And then we have to divide that by another integral over d phi of e minus s CFT plus h o. Okay, so this is the full path integral that defines the problem. So this is for not counting vacuum diagrams, and then we average the result as before. So now one can make a simple dimensional analysis argument. So let's suppose, the natural dimension that you want to associate h with, so that this thing is marginal, is d over 2. Okay? If h had dimension d over 2, then this would look like marginal, and c would look dimensionless. So h has dimension d over 2 naturally, and this has dimension delta. And in this convention, you see that this coupling is relevant if delta is smaller than d over 2. So you find this critical number, which is d over 2. And so if delta is smaller than d over 2, you would either get new critical exponents or maybe even kill the whole CFT, as we've seen before. But if delta is smaller than d equal to, if delta is bigger than d equal to, then you expect that this disorder in H would be relevant. So it won't change the critical exponents. Okay, so the critical exponents would remain, the phase transition would remain, and you would essentially get the same result as for the pure theory, without any disorder, same as the pure theory. But if the dimension is smaller than d over 2, we don't know. Okay. It might either change the critical exponents or it might kill the whole CFT, and one would need to find what are the general conditions for either of that to happen, but it's not known. This fact is called the Harris bound. It's a central result. You see, that's completely trivial in a sense. It's just dimensional analysis, but it's important that d over 2 is the decisive dimension. Are there any questions about that? So the interesting question lies here of under what conditions do you get maybe just the change of the critical exponents, or otherwise the whole theory disappears? How much more time do I have?
The marginal case?
Yes, we'll discuss that also. How much more time do I have?
Another 45 minutes.
Okay. Yeah, so let's also discuss separately the marginal case. So let's discuss separately the marginal case. This is when delta is exactly d over 2. And, well, experience with conformal field theories would suggest that that probably it's irrelevant. But experience with conformal field theories with problems which smell a little bit similar suggests that the marginal case should be similar to the irrelevant case. So perhaps this is marginally irrelevant, and you'll see that indeed this is the case in an example that I will study momentarily. That's what you would expect, even though I must admit that I'm not completely sure that this is the general answer. I have some doubts, but at least in some example that I will study now in detail, this is what comes out. I have some doubts about whether this is completely correct always or not. Okay. That's what you would expect, I think, naively, but it remains to be seen. Okay, so how do we tackle this problem? Well, one class of theories which can be solved is large N. We can just solve large. We can take a classic. We can study large N field theories which I'll explain now. And we can just solve this case and see what do we get. Okay, you'll see what the answer is. You can compute the numerical exponents when there are numerical exponents, and you can find the precise condition for which you lose the CFT. Yes.
What happens if the symmetry got broken is local instead of global? With what you said is still true.
Oh, you meant in the qualitative argument about the breaking of the global symmetry below 4 dimensions. So you are asking what would happen if that symmetry was a local symmetry, like a gauge symmetry, you mean? So I don't think gauge symmetry means anything. It's just a redundancy in the description. It has no physical content. You see what? No, I don't think it would matter at all. Okay, so let me just review now large N quantum field theory. That's something that would be useful for you to know if you don't already know, regardless of any of that. And the utility of large N, in the context of this problem is that this question can be settled. This question can be settled for the better or worse, and you can try to compare with experiment to see if it, at least qualitatively, looks similar to what experiments measure. There is lots of experimental data in this field, very little theory, comparatively speaking. And at least you can try to compare and see whether it makes sense or not. So large N. So let me explain the basics of large N field theory in some general fashion. There are several kinds of large N models that you would find in the literature. There are vector models, and I think Shiraz is going to talk a lot about those, right? So there are vector models, and then there are adjoint models. So, for example, an example here is n equals 4 in the 'Hooft limit, or QCD, for that matter, in the 'Hooft limit. An example of a vector model is phi squared in the limit where phi is a very long vector. And they are both large N models. They have some differences, but there is one thing that is common, which is that they can be described in the strict large N limit using what's called generalized free fields. So I'll introduce this notion. Generalized free fields. So this is something that's common to all the large N models, and you can study large N field theories regardless of the details using this concept of a generalized free field. So what is a generalized free field? So a generalized free field, or also GFF, I'll refer to it as GFF. So a generalized free field is an operator O of a dimension delta, such that its 2-point function is fixed by conformal invariance to be 1 over x to the power 2 delta, and higher point functions of O, so x1, xn, are given by sums over choices of permutations when you just take two O's, let's say OX1, OX2, and then you divide it into a bunch of pairs. So you just do weak constructions. So the idea of a generalized free field is that even though it's not a free field because it has anomalous dimensions, right? So there is a certain anomalous dimension delta which doesn't have to be that of a free field. You can still apply the weak theorem for endpoint functions. So this is the definition of a generalized free field. Now let me say a few things about generalized free fields. So let's study their 4-point function. OX1, OX2, OX3.